Okay, so today we are going into the last chapter that we'll be doing in this course. So we'll be doing sequences and series of functions. So chapter 7. Sequence and series. And now functions. Okay. So you want to think of this sort of like, just like you were thinking about sequences and series back in chapter 3, but now each of the points in your space is actually a function. Okay, so we'll start off with we're going to talk about two kinds of convergence. The first is called pointwise convergence. So pointwise convergence, and so that's, well, the idea is like this. You have a bunch of functions, right? So let me set things up properly here. So you have a metric space, and you have a subset of the metric space, and then you have a collection of functions that are complex valued. Okay, so you have a bunch of functions on your metric space. They're complex valued functions. Okay. Okay. So if the limit of f of x, f of n of x, as n goes to infinity, exists for each x in E, we say that this thing f sub n converges pointwise on E. Okay, so let me it's not too fancy. Let me show you a picture. So here's an example. If we look at f sub n as x to the n on, say, 0, 1. Okay, so let's suppose we're looking at the interval 0, 1, and we're looking at these functions that are just x to the nth power. Okay, so for n equals 0, right? For n equals 0, that's just the constant function 1, right? For n equals 1, that's your function f of x equals x. Then you've got x squared, right? X cubed, right? X to the 4th, and so on and so forth, right? Okay, and you see that if you take the limit of x to the n as n goes to infinity, what do you get? What happens at each of the points? Well, what happens at 1 first? What do you get at 1? 1 to the n as n goes to infinity? 1. Okay. So so this guy is going to be 1 if x equals 1. Okay. But what if x is smaller than 1? Between like it's, of course if it's 0, it's 0. What if it's between 0 and 1? Well, as you take powers of it, n goes to infinity, you end up with, let me just say it. Charlotte?
What?
You take a number between 0 and 1, and then you take the nth power of it. You take its nth, raise it to the nth power, and let n go to infinity.
It goes to infinity.
Oh, sorry. Well, it's smaller than 1. So, like, suppose you take a half.
Oh, so it goes to 0.
It goes to 0. Yeah, it goes to 0. Okay, so it's 0, right, otherwise. Right, so what you see is that, for every point in 0, 1, this has a limit, right? So this converges, this sequence converges pointwise to this function f of x is 1 if x is 1, and 0 if x is between 0 and 1. Okay. So Julie, we're just talking about this notion of pointwise convergence. Okay, so you've got a sequence of functions, and at every point, the limit of the sequence of functions converges to something. So the example here is like x to the n, right? X to the n on 0, 1, and if you let if you take a point, if you take say 1 and let n go to infinity, it's just going to be 1, right? But if you take something smaller than 1 and let n go to infinity, it's going to go to 0. Right, so this sequence of functions, right? So this sequence f1x equals x, f2x equals x squared, f3x equals x cubed, et cetera, converges to this function, right? 1, 1, 0. It's 1 at 1 and 0 everywhere else. Okay, so this is an example of so-called pointwise convergence. Okay, and okay, I'm not going to explain it again. You ready, everybody? Yeah. Good. Okay, so yeah, and similarly, right, if the sum, right, if the infinite sum, converges at each point, again, we say that this infinite sum converges to some function. Converges pointwise. Okay, so you can talk about a sequence converging, you can talk about a series converging. Okay. Okay, let me make a comment here that you notice that Remark, the Fn are all continuous, right? The Fn are all continuous, but the limit is not continuous, right? So even though you've got all these guys are continuous, their pointwise limit need not be continuous. So continuity isn't preserved when you take the pointwise limit. But the limit is not. Okay. So pointwise convergence doesn't preserve continuity. Let me give you another example that Reardon gives. He says, well, let f sub n be x squared times 1 over 1 plus x squared to the n. Okay. For n equals 0, 1, 2, etc. Okay, so this is just a rational function, right? It's a rational function, and you see that it has no zeros in the denominator, right? It's equal to 0. It's equal to 0 at 0, but it has no vertical asymptotes, right? Okay. Now let's consider the sum here. Right? Well, that's going to be x squared summation 1 over 1 plus x squared to the n. And it's from 0 to infinity. Okay. But this is a geometric series, right? This is a geometric series, and so you get some, or 1 over 1 minus the ratio. Oops, what's that I'm doing there? which turns out to be, when you work it out, it's just 1 plus x squared. Actually, that's not quite right. That's not quite right. Because at 0, at 0, this thing blows up, right? At 0, you get this thing. You get the sum of ones. Right. But okay, so this is for x not equal to 0. Okay, and then for x equals 0, what do you get? Well, you're going to get look at what the partial sum series is going to be. It's going to be x squared times this thing, right, times the partial sum. Right, but that's just some number. It's just going to be, k times 0. Right. When x is equal to 0, you're going to get 0 times, a sum of ones, right? A finite sum of ones, right? So that's just going to be 0. Okay. So the partial sum sequence for this series is just 0, 0, 0, 0, 0, 0, 0, right? So in that case, this thing is 0. Okay. So what's the point here? The point is that if we look at the infinite sum, it looks like 1 plus x squared, right? Which is just this parabola shifted up by 1, right? With a discontinuity at 0, right? Because at time 0 it's 0, but here it's outside of that it's 1 plus x squared. Okay, are you guys okay with that? Yeah. Right. So here's the infinite sum, and so this is kind of interesting because each of these guys is continuous, right? Each of these guys is continuous. But when you take your sum, you get something discontinuous. Okay, so it's even the case that even if you have a bunch of continuous functions, their infinite sum might not be, even though it converges pointwise to this, their infinite sum is not continuous. So continuity isn't preserved. Okay, are you guys, I hope you're getting the idea of pointwise convergence, right? Pointwise convergence just means that you've got some sequence, and then you take the limit at each point, right? The limit at each point. Okay. So let me give you a non-example. So something that doesn't pointwise converge. This is something that my professor showed us when I was taking a course in real analysis. So here's a non-example. And it is what he called the blimp functions. Okay, so this is kind of funny. So you restrict yourself to 0, 1. Okay, and the first function is just going to be 1 everywhere. Okay, it's going to be 1 everywhere. The second function is going to be 1, but only between 0 and 1/2. Okay, the third function is going to be 1, but only from 1/2 to 1/2 plus 1/3. So it's 1. So it's going to be 1 here, right? So the length here is 1, the length here is 1/2, the length here is 1/3, and you can guess what's going to happen, right? So the next function is going to be, it's going to be 1 on an interval of length 1/4, right? And then next on interval of length 1/5, and so on and so forth. Okay, but the rule is that if you go beyond 1, you wrap around. Okay, so if you go beyond here, you wrap. So if like, if you have some interval, if I have some interval, here's 1, it's like, it's length 1/n, right? I'm gonna just wrap that around, and the blimp will be in 2 pieces, basically. Right? That makes sense? Right? It's like an old video game where you go off the right side and you come back on the left side, right? Asteroids, say. Okay. So, now the blimps are shrinking. The blimps are shrinking in length, right? The blimps are shrinking in length, but what's the sum of 1 plus 1/2 plus 1/3 plus blah 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 blah? What happens to that sum? It diverges, right? It goes. It's infinite, right? It goes off towards infinity, right? By p-test, say. Okay, so what that means is that, even though the blimps are shrinking in length, you never stop seeing blimps, right? You never stop seeing blimps, because if you lay the blimps all in length together, right? It's an infinitely long line of blimps, right? The total length of the blimps is infinity, right? And so you're never going to stop seeing blimps. Okay, so in other words, if I choose a point here, it's like, oh yeah, I see the blimp. I don't see the blimp, right? I see the blimp. I don't see the blimp, right? And the time between seeing blimps gets longer and longer, right? Because the blimps are becoming shorter and shorter, right? But you never stop seeing blimps, right? So the value at this point, so f1 of x is 1, f2 of x is 0, f3 of x is 1, f4 of x is 0, right? And so you have the sequence 1, 0, 1, 0, right? And the space between the ones gets longer and longer, but it never becomes 0, 0, 0, 0, 0, 0, 0, right? Right, and because of that, this sequence doesn't converge, right? Because you might, if the blimps shrank really quickly, right? Then if the blimps shrank really quickly, then it would converge to 0, basically, right? Every point you can make it so that every point eventually just gets zeros forever, right? But because the blimp's total length is in infinity, no matter how far along the line you are, as long as you keep on waiting, the blimp is going to show up, right? So you're going to get a 1 eventually. There may be a bunch, there may be tremendous number of zeros, but then you're going to see a 1, and then there'll be like order of magnitude of zeros even before you see another one. Okay. So this. You see that this sequence doesn't converge pointwise anywhere. Okay. So these guys don't converge pointwise. Okay. Which is kind of interesting, because you would think that, look, after a long period of time, right, the difference between your function and the 0 function is very tiny, right? So, shouldn't that count as some sort of convergence? In fact, there's a different kind of convergence called convergence in measure. These guys converge with respect to that different notion of convergence called convergence in measure, which you will see if you take a course like 137, which is being offered next semester. Okay. Okay, so what's the point here? The point is that we have this notion of pointwise convergence, and it's a little bit unsatisfactory in that, one, it doesn't preserve continuity. Other things that it doesn't preserve are like integrability and differentiability. You can have differentiable functions whose limit is not differentiable. You can have integrable functions whose pointwise limit is not integrable, and so on and so forth. So the things go kind of bad. Let me give you some examples of sort of badness of how pointwise convergence and basic calculus concepts. So here's one example of Rudin's. He says, consider this function, f of n is 1 over the square root of n sine n x, n being 1, 2, 3, etc. Okay. If you differentiate that, you get square root of n cosine nx. Okay. Now, if you take the limit of these functions, what happens? What's the pointwise limit of the f sub n's? Right? You got a bunch of sine functions. The sine functions are divided by 1 over the square root of n. As n goes to infinity, what's going to happen? Anybody have an idea? Anne, go ahead.
Is it going to go to 0?
It's going to go to 0 because sine is trapped between -1 and 1, right? Sine is a bounded function, and then this thing you're dividing by becomes it becomes huge, right? So this is going to go to 0. Right? So you take the limit. The limit of the f sub n x is just the 0 function, right? So right, it's constantly equal to 0. Okay, so if I take the limit, I get this. If I differentiate it, right? If I differentiate the limit, of course I still get 0, right? So the limit, if I take the limit of these guys and then I differentiate, I get the 0 function, right? Suppose I differentiate first and then I take the limit. If I differentiate first and then I get the limit, then I don't get the 0 function. Very much no, right? Right? As n goes to infinity, I get this huge function here, right? Right. So so what you see is that the limit and differentiation don't commute. Okay, so the limit of the derivative is not the same as the derivative of the limits. Let me give you another example. So if I take, say, so this is kind of a simple one, fnx to be the characteristic function of the interval n plus 1. Okay. I don't think I've used this term before. Characteristic function means it will give you a 1 on this set and it'll give you 0 elsewhere. Okay. So this is the function that basically tags you if you are in that specified set. Okay. So here's the characteristic function. F sub n is the characteristic function of n plus 1. Okay. So okay. So what's the integral of this function over the real line? So it gives you a 1 if you're in this interval, and it gives you 0 otherwise. What's the integral of this function?
1
1. Yes. Right? The integral is 1. Right? And if I take the limit of those integrals, I still get 1. Right? Okay, but suppose I try to take the integral of the limit. Okay, well, if I take the limit, what's the pointwise limit of this function, of this sequence of functions? I take a point x, and then I take the limit of these characteristic functions evaluated at x, and let n go to infinity. What's it going to be? Talk to a neighbor for, I'm going to go outside for a minute. Talk to a neighbor.
I thought it's just like
Because
1
the
or
limit
0.
is 0. Yeah, because x stays in place, but it'll keep going.
I guess it could be 0, right?
Yeah, but I feel like it's got us here negative 0.
And
So it would just
okay.
try to not go see.
Okay, what's the answer? Nobody knows the answer. Nobody's willing to, nobody knows the answer. So I just think, right, like, you've got this point, let's say it's 10, okay, right? What's f1 of that point? f1 is the guy that says, are you in 0, 1? I'm sorry, no, it's not. It's, are you in 1, 2? And he says, no. Okay, so you get a 0. The first thing you get is 0. Are you in 2, 3? No. Are you in 3, 4? No. Are you in 4, 5? No. Right? At f10, it's going to say, are you in, well, actually at f9, it'll say, are you in 9, 10? Yes. Are you in 10, 11? Yes. Are you in 11, 12? No. 12, 13? No. No. Right? Right? So it's going to, the limit is 0. Right? Whatever point you choose, the blimp is going to pass you by. Right? You'll be 1 for, for at most 2 blimps. But that blimp just keeps on going, and after that, you're 0. You're nothing. It's sad. You had your 1 moment of glory, or maybe 2. But then after that, you're 0. Okay, right. So the limit it's the integral of 0, right? Which is just 0. Okay. So the point is that what's the point? The point is that again, these things don't commute. Right? You can take the integral, the limit of the integrals and the integral of the limit, and they get completely different answers. Okay. Okay. Yeah, and actually these two problems are kind of a lot of what is dealt with in 137. In addition to creating a completely different way of integrating integrals, called the Lebesgue integral. Which is part of why I don't, I think it's more important to do chapter 7 than chapter 6 on the Riemann integral, because we're going to throw away the Riemann integral once we go a little bit farther. In any case, this is important stuff. Okay. So what's the point? The point is that pointwise convergence actually doesn't interact well with basic ideas of calculus. Okay. But there is something that does work well with the basic ideas of calculus, and that is so-called uniform convergence. Okay. So that's something a lot stronger. Okay. So So first off, here's a little exercise. How would you write Fn converges pointwise to F on E in epsilon n language? How would you write that? Take a minute and write something down. Okay, so would anybody like to say what they wrote down? Right, f sub n converges pointwise to f, right? Right, what does that mean? That means that at every point you've got convergence, right? So let's just write it down, right? At each x in E, the limit of fn x equals f of x as n goes to infinity. So this is not using epsilon in language yet, but this is the idea, right? This is what pointwise convergence means. At every point, you have convergence, right? So just take this thing, translate it, right? The limit of that is that. In other words, given any epsilon greater than 0, there exists a time such that if you're past that time, then the distance between fn x and f of x is smaller than epsilon. Okay, so that's the definition. Right, that's the language, right? At each x and epsilon, for each point in the set, given any epsilon, there exists an n such that blah, 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 right? And notice that this n, just to make it explicit, this n depends on the epsilon, but it also depends on the x, right? Okay. Okay. So now we're going to give something called uniform convergence. You have some sequence. We say f sub n, the sequence of functions, converges uniformly to f on E if, can anybody guess? Anybody guess what I'm going to say here? Converges uniformly. Right. Go ahead.
Is it if the same delta works for all x's?
Yeah, the same delta, but it's an n
Oh,
here.
sorry.
Yeah, exactly. So works independently of x. Exactly. Right. So if given any epsilon, there exists an n such that if n is bigger than n, then the distance between fnx and f of x is smaller than epsilon for all x in your set. Right? So this thing happens everywhere. Okay. Right. So this is a very, 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 very different condition. Right. So here, right, here what we're saying is that there's an n that works for each, for each point, there's an n that works. And here what we're saying that there's an n that works for all points, right? Okay. The picture you want to keep in mind is the following, right? Let's say that you have some, here's your E, okay, and here's your F, okay. What it's saying is that given any epsilon, there's a time past which all the values are within epsilon of f of x, right? What that means is that if you look at this tube, f of x, f plus epsilon, f minus epsilon, right? It means that there's a time past which everybody's in the tube, right? So given any epsilon tube, there's just a time past which all graphs are in the tube. Okay. Okay. So for example, here's a non-example of uniform convergence. These guys that we looked at earlier, x to the n on 0, 1, right? So actually, let me make it on 0, 1, the open set. Okay. Okay. So what do those guys look like? Right. Actually, I'll just make it completely open set here, like that. Here's the first guy. Here's the second guy. Here's the third guy. Here's the fourth guy. Here's the fifth guy, and so on and so forth. Right. Now, pointwise, right? These guys go to 0 pointwise. Right? At every point, eventually it's going to go to 0. Right? So the limit is the 0 function. Right? The limit is the 0 function. But they don't converge, these guys don't converge to 0 uniformly. Because you can kind of see that, because look, no matter, like if I take an epsilon tube around here, I take an epsilon tube around the limit, right? I can't find a time past which everybody is in the epsilon tube, right? At some of these guys, maybe you can get the first million of them in, but eventually they're going to start jumping out at the end. Okay, so yeah, so that's a non-example. Okay. Okay. So uniform convergence, the idea of a tube. There's another really useful way of thinking about uniform convergence. Actually, before we do that, let me give the Cauchy criterion. So, Cauchy criterion for uniform convergence. Okay, and this is basically what you would expect. So you have some sequence of functions. for some sequence of functions, f sub n converges uniformly on E if and only if can anybody guess what this is going to be? Converging uniformly on E, right? We want to think of it in terms of the Cauchiness. Bond, go ahead.
It is a distance between two.
What?
It is a distance between two points, like two points, approaching zero.
Yeah, yeah. So you say, if, given any epsilon, there's this time such that if n and m are bigger than that time, then the distance between them is smaller than epsilon for all x in E. Right, so it's just the Cauchy criterion, right? It's just the Cauchy criterion, but applied uniformly, right? There's an n, right? This n depends only on epsilon, not on x, right? So there's an n, oops, should be over here. There's this an n, dependent only on epsilon, so that if you're beyond that time, then this is true at every point. It's it's kind of what you would expect, right? And similarly, right, we say this thing, a series converges uniformly. You can have a Cauchy criterion for series, same sort of thing, right? Given any epsilon greater than 0, there's this an n dependent on epsilon, such that if you have two indices beyond n, then the size of the tail is smaller than epsilon. Okay, I think I'm going to leave this to you as an exercise. Okay, so I'll read the proof yourself. This is a pretty straightforward proof. So I think you can do it. I want to get to a very useful theorem called the Weierstrass M-Test. So this is a theorem that if you do more analysis, you'll definitely see this. This is used all over the place. We'll use it in the complex analysis course this fall, for sure. So here it is. So again, you have a sequence of functions, complex valued functions. And it says that if you have, all of those functions are bounded, suppose each of those functions has a bound, okay? And the sum of the bounds is finite, right? So this thing converges. Then your sequence of functions converges uniformly.
Did you say the sequence or the series?
I'm sorry, your series converges uniformly. Your infinite series converges uniformly. Okay, so this is like a condition to check whether you've got uniform convergence. And this is very, very handy. Okay. Okay. So yeah, this is it's a simple tool, but it's an extremely useful one. It's used quite commonly. So let's do the proof. Proof is we're going to use the Cauchy criterion. So use the Cauchy criterion. Right. Fix epsilon. Okay. So can anybody see how we might do it? Right? We want to find an n past which this thing is smaller than epsilon. The size of the tail is smaller than epsilon. We want to find an n past which the size of the tail is smaller than epsilon. What do we have? We have that each of those terms is bounded, and the sum of the bounds is finite, right? So this thing converges. How are we going to get an n? How do we find an n so that this thing, right? We want an n past which this thing is smaller than epsilon. And that's our goal. And go ahead.
Does the fact that the series of mn's converges mean that mn goes to 0? Is that useful?
The mn's go to 0. It's true. It's not what you want.
Okay.
Yeah. It's not what you want because the fact that those terms go to 0 is still tricky because you're going to be summing these guys, and there could be many of them, right? There could be a whole bunch of them. Even if the terms are small, you've got too many to handle.
Okay.
Yeah. But you're on the right track. Yeah, this thing converges. So you're going to use the Cauchy criterion. We'll use Cauchiness. Since this thing converges, we know that this guy's tail can be made as small as we desire, right? We know that, so what's the point? Since these guys this is convergent, we know that there exists an n such that if n and m are greater than n, then this guy, this tail, is smaller than epsilon, right? That's the Cauchy criterion for series of numbers. Okay, but then this thing here, right, fkx from k equals n to m, that's going to be smaller than the sum of the absolute values from n to m, which is smaller than the sum of the m sub k's from n to n. Right, by boundedness. Right, so triangle inequality gives us this. Boundedness, right? Boundedness, the assumption of boundedness gives us this, and this is smaller than epsilon. Okay. So that's it, Weierstrass M-Test. Okay. So don't forget it. It'll be, if you go on analysis, you're gonna see it. Okay, that's it for today. Next time, we'll talk about, the next couple classes are gonna be, I'm afraid, kind of dense. So I suggest looking at the text in advance.